In this video, we're going to be calculating units of G, otherwise known as the G force. So if you have watched the PowerPoints for Chapter 2, you probably saw this problem presented to you on the PowerPoints. So this problem was an actual experiment done by Colonel J Stapp in order to improve the harnesses on fighter jets. Colonel J Stapp conducted experiments using a sled that was traveling at different velocities. So his goal was to see what the human limit of acceleration and what the human limit of deceleration was. So basically, how quickly could a human come to a stop without it causing detrimental damage to their body. So he did these experiments basically to see if the use of an ejector seat would be helpful in fighter jets or not. Because if the body couldn't handle decelerating at a certain rate, then the ejection seats would be pointless. So he wanted to prove that the human body could withstand certain amounts, thus making better equipment in these fighter jets, harnesses included, as well as ejector seats. So in his experiments, the highest velocity that he reached on this sled, and it was actually him in the sled during this particular experiment, was 283 meters per second. So that was the initial velocity, because we're starting at 283 and then the sled is coming to a stop. It's coming to a stop in less than a second, so 0.624 seconds. So we're going to calculate the deceleration and then the G force, or the units of G. So let's start by calculating the deceleration. So this is something we've done before in previous videos. So in this particular problem, there is an initial velocity. So the object is initially in motion. So we're going to use the non-zero initial velocity equations. So this first value here of 283, because remember the first step is always to label our knowns and unknowns. So that 283 meters per second, that is going to be an initial velocity. So I'm going to do that v sub I. The sled came to a stop. So since it came to a stop, that tells us what our final velocity is. That's going to be 0. And then it also gives us 0.624 seconds, which is a time. It wants us to calculate deceleration. And remember, deceleration is just the slowing down version of acceleration. Okay, so it's still A as our unknown that we're calculating. The second step is always to convert if necessary. In this case, we don't need to, so I'm going to put a check mark because we have our units in meters per second for the velocities and in seconds for time, so we're all good there. Our third step then is to find an equation. So we've already said that this is a non-zero initial velocity problem, so those are the equations we would look towards. We would want to pick the one where acceleration is equal to, and in this case it's going to be final minus initial divided by time. So this is the equation I would choose. Now I'm going to plug in my values. Forgot my calculator here. So it's going to be 0 minus 283. So it is going to be a negative number, which makes sense because we always want a negative value when we're talking about deceleration. So we're going to get negative 283 divided by 0.624. When we solve, we just said we're going to get a negative, and we're looking at 3 sig figs in our answer. So it's going to be negative 450, and we'll round that up to a 4. The units on acceleration are meters per second squared. So I'm going to plug that in over here. Now when Colonel J Stapp did this experiment, he survived. Okay, so he realized that the human body can slow down at this rate without dying. However, there was a lot of damage to his body. I believe he passed out during the experiment, which makes sense because when you're decelerating at a high rate, what's happening is your blood is rushing to your feet. And with your blood rushing to your feet, it doesn't really give enough blood to make your heart beat as fast as it should, so your heart rate's going to slow down, which often causes people to pass out. Also, he broke all the blood vessels, not all of them, but several blood vessels in his eyes. He went temporarily blind. Lots of other things happened as well. So there was damage to his body, but the fact is he survived. So what we're going to do next, since we calculated the deceleration, is now we're going to look at calculating the G-force. So this is something new that we haven't done before. So I'm going to erase this section here so we can use it to calculate the G-force. So for the G-force, or units of G, the equation that we're using is we're going to take the acceleration and we're going to divide it by 9.8. So G-force, G standing for gravity, units of gravity or gravitational force. So the units are meters per second squared on this bottom portion. So the reason we're taking acceleration and dividing it by 9.8 meters per second squared is because 9.8 is the value of gravity. So we're trying to figure out how many units of gravitational force, or how much units of gravity. So why do we calculate G-force? Well, G-forces are used to convey values of force and acceleration. So G-force can be related to roller coasters. It can be related to fighter jets, like here. It can be related to other sorts of rides. It can be related to rockets. NASA uses G-force. So lots of different areas use G-force. So as an example, let me write off to the side. The average roller coaster their goal is to stay in the range of 4 to 6 G's as a max for acceleration. They tried to stay in the range of 1.5 to 2 G's for deceleration. So notice, since there's a negative number in front of these, this would be deceleration, positive number, this would be acceleration. So this is the ranges that the roller coasters like to stay in. So when I'm talking about 4 to 6 G's increasing, that's when the roller coaster increases and you feel heavier. So when the roller coaster starts going and you're pushed back into your seat, against your seat. Or if you're looking at a roller coaster going up in the vertical direction, that would be the extra weight that you feel added, pushing you down into the seat. For these negative G-forces, so this is when a roller coaster is coming to a stop, or if it's if a roller coaster is coming to a stop, this would be a feeling of weightlessness, where you feel like you're coming out of your seat. Okay, so notice they want a smaller number for the weightlessness factor, and that probably has to do with the harnesses that you're using at roller coasters, versus you could have a higher rate or higher G-force when you're feeling that added weight, because that added weight that you're feeling is going into the seat that you're sitting in. So not as dangerous, so you could have higher values here. All right, so with this comparison kind of being set, let's calculate the G-force in this experiment. So it's going to be much, much higher than these values, because when you're on a roller coaster, you don't have blood vessels breaking, right? It's not high levels. Whereas here, he did experience that. So to calculate the units of G, or the G-force, we're going to take our acceleration that we had down here, -4.54 meters per second squared, and I'm going to divide it by 9.8 meters per second squared. Now notice, I'm dividing so the units are canceling. So this is a unitless number. So we have 454 divided by 9.8, so I'm going to get negative 46.3 units of G, or G's. So compare. I just went single digits into double digits. Okay, so this is a lot of force that was being applied, hence all of the injuries that Colonel J Stapp got during this experiment. So what I want you to do for the challenge in the discussion this week is I want you to find the acceleration of an object. Okay, so this is something you can Google. It can be the acceleration of an airplane, a space shuttle, like a baseball, like a fastball, or a football, train, human, car, bullet, bicycle, elevator, anything. Okay, so find an acceleration. It can be an average acceleration, or it can be the highest recorded acceleration of any of the objects. What I want you to do is I want you to take that acceleration and calculate the units of G. So it's pretty straightforward calculation. You're going to take the acceleration you found, divide that by 9.8, and then tell me how many units of G that particular object has. So what's its G force? That way, when people go through and look, they can compare it to our extremes. We have a roller coaster on the low end, and then we have Colonel J Stapp with the fighter jets on the other side. Okay, now the acceleration you choose, it can be an acceleration, so how fast did it speed up, or it can be a deceleration, how fast that object, or at what rate that object slowed down.